Hello, I'm Seema and welcome to part 6 of the topic Acids and Bases in Organic Chemistry. In the past few videos, we have been using the mnemonic CARIO in order to compare the acidic and basic strength of organic compounds. In this video, I will be discussing the last step in CARIO, that is O. O stands for the hybridization of the orbital that has the acidic hydrogen attached to it. Let us now see how the orbital affects the hybridization of the atom affects the acidic or basic strength. We take 3 examples here, that is ethane, ethene and ethyne. Now, any compound can be made to act as an acid by removing a proton or by adding electrons from it. And therefore, whether it naturally has a tendency to do it or not is not the question. It is possible to make a compound act as an acid. And if it is possible to do that, it's also possible to compare their acidic strengths. So we deprotonate these 3 compounds to get their conjugate bases. And when we do this, what do we see? The charge on each one is the same, that is -1, and all 3 of these were neutral. The atom bearing the charge is carbon in all the cases. And the resonance, there is no resonance that we see here because there are no alternating bonds. Then we have induction. Induction, again, is not possible here because they are all carbon atoms. It's a chain of carbon atoms and we do not see another electronegative atom anywhere around. So we now come to the last part of the mnemonic CARIO, that is orbital. What's the difference between the orbitals of these 3 carbons which have deprotonated? This carbon is sp3 hybridized, or you could say this also, the structure becomes clearer here. This is sp3 hybridized. This carbon is triangular planar and it is sp2 hybridized, while this carbon has sp hybridization, right? When we look at the 3 hybridizations, that is sp, sp2 and sp3, what do we notice? sp, sp2 and sp3. sp is made up of 1 s orbital and 1 p orbital. sp2 is 1 s and 2 p orbitals, so it will be s, p and p. sp3 would be s, p, p and p. So if we want to find out the percentage of s character in each one of these, why do we do this? The s orbitals are smaller in size and they are closer to the nucleus. The electrons present in an s orbital are closer to the nucleus. And p orbitals are the shapes of dumbbells and they are a little away from the nucleus. So when s and p hybridized, the amount of s character makes the electrons come closer to the nucleus, but the hybridized orbitals are all identical. sp means there are 2 orbitals which have s and p character. sp2 would be 3 orbitals with sp and 2p characters, and sp3 would be 4 of them. But each one would be identical. sp has 2 orbitals which are identical. These are 3 orbitals which are identical. These are 4 orbitals which are identical. But the amount of s character makes the orbitals, the hybridized orbitals, smaller, or the electrons of the hybridized orbitals would be closer if the s character is more. So how do we find out the s character? In sp, if we want to calculate the s character, we write s upon s and p, right? So there are only 2 types of orbitals, s and p. Out of these, the s character is half of it. So we say that sp character is 50%. 50% of sp would be s character. In sp2, the s character would be spp. That is, it is only 1/3, which means it is 33%. You have 33% s character. In sp3, you would have s upon spp, which is only 25%. So s is only 1/4 of the orbitals. The s character is only 1/4 of all the orbitals. So what does this show? it shows us that in an sp3 orbital, although all the 4 sp3 orbitals are identical, the s character is the minimum, which means the tendency to pull the electrons towards the nucleus is the least in sp3 orbitals, while in sp orbitals, the tendency to pull the electrons towards the carbon nucleus is the most. So when deprotonation occurs, this carbon is sp hybridized. So these electrons will be closest to the nucleus of this carbon. If they are closest to the nucleus of this carbon, it means that this should be, the conjugate base should be stable, because the electrons are being attracted more strongly by this carbon in comparison to this one. Right? So we say that this one is most stable. And if this is most stable, what about the sp3 hybridized one? In sp3 hybridization, the s character is the least. Therefore, the electrons are least close to the nucleus. And therefore, out of these 3 conjugate bases, this one should be the least stable. If it is the least stable, it means it has the tendency to recombine with H positive to give you back the alkane. And you know, actually, this species is very, very rare. It's not easy to form this. I wouldn't say rare, but it's not easy to form this because it is so unstable. So we find that if this is the most stable, then this is the weakest base. And as a result, the weakest base, conjugate base, would be the strongest acid. And this is the least stable. It means it is the strongest base, while this would be the weakest acid. And this falls in the middle. It is in the middle, both as the acid and the base. Right? So on the basis of this, what do we see about the acidity? That if you follow the acid strength, Sp, Sp2 and Sp3, the acid strength what would be the direction of the acid strength? The strongest acid is the one with Sp. So acid strength increases. If you go from Sp3 to Sp, the acid strength increases in this direction. And if acid strength increases in this direction, the basic strength should be the opposite. So basic strength should increase from Sp to Sp3. This is what we understand from this hybridization. That when you have a Sp hybridized carbon atom, or an atom which is Sp hybridized, it would form the weakest base, it would form the most stable conjugate base, and hence the acid would be the strongest acid. And if you have the least stable conjugate base, you would have the weakest acid. Let us now come to the second example. Look at this compound. This carbon here has a triple bond. Therefore, this is Sp hybridized, and this carbon of the benzene ring should be Sp2 hybridized. Right? And in toluene, this carbon here is Sp3 hybridized, while the carbon here is Sp2 hybridized. So, although both are carbons, the Sp hybridized carbon has more S character, and therefore it has a tendency to pull the electrons towards itself. And therefore it would be, and the Sp2 carbon on the other hand does not have the same tendency to pull the electrons towards itself. And Sp3 on the other hand has the least tendency to pull the electrons towards itself. So how does this affect both these compounds? It's really interesting. In this compound, the Sp2 to Sp3, where do you think would the electrons tend to, which is more electronegative? This carbon, Sp, is more electronegative, right? it is electronegative and this is electropositive. But here in this example, the sp2 is more electronegative in comparison to sp3. Here sp3 is electropositive. Do you see the difference in both these compounds? So what happens as a result of this? We find that in comparison, if this carbon is more electronegative and this is less electronegative, this carbon would have a tendency to pull the electrons towards itself, thereby making the conjugate base unstable. Because when it will do that, the hydrogen which is removed, the negative charge would get more negative charge, making the conjugate base unstable. If the conjugate base would be unstable, this would be the weaker acid, right? And on this side, you see toluene. In toluene, what is happening is that this is more electropositive while this is electronegative. So it has a tendency to pull the electron towards itself. So when a proton leaves, the electrons will have a tendency to be pulled towards the benzene ring, thereby imparting it more stability. And because it would now participate in resonance. And therefore, this would be more stable at the conjugate base, and hence it would be the stronger acid. Now it's really interesting to see here that in this example we cannot use the mnemonic CARIO in isolation. We don't use just the orbitals. Here we find the effect of resonance too, and we also find the inductive effect. If you really see, when this is more electronegative, it means this is showing a minus I effect, and the benzene ring is showing a plus I effect, right? But in this, in toluene, it is the benzene ring which shows minus I effect and the methyl group which shows a plus I effect, right? So you don't have to use just one of these steps in mnemonics. What happens? You either go stepwise, but many a times you have examples or you have factors, more than one factor which affects the acidic or the basic strength. And in some compounds, the entire mnemonic falls short of explaining the reason between the acidic or the basic strength. In such examples, we have to delve deeper and understand what causes the difference in their acidic or basic strengths. But isn't this interesting? Here, how you have the same carbons, but the hybridization affects the inductive effect too. And therefore, you can judge the acidic or basic nature on the basis of that. Let us now take one more example here. We have these two compounds and we have to compare their basic strength, right? Here you have NH2, which is connected to cyclohexane, right? And here you have NH2 attached to a benzene ring. So the difference is that here you do not have a benzene ring, it's a cyclohexane molecule, and here it is a benzene ring where resonance is a factor. So if we try to compare these two compounds and you use the mnemonic CARIO, we find that both have the same charge as bases. Both have nitrogen, which is bearing the electrons, that is the atom bearing the charge should be nitrogen. Resonance, one of these shows resonance and one does not. And induction, we need not consider that here. Let us come to the orbitals. What is the difference between the orbitals here? Is there a difference first of all? Or if you just look at it, there appears to be no difference. The nitrogen here is sp3 hybridized and the nitrogen here is also sp3 hybridized. But as soon as the electrons of nitrogen, they participate in resonance with the benzene ring, which is possible, the electrons here, they can move to form a bond here, and therefore it would push these electrons here, forming a bond here, which would in the next step move on to the next, and then these electrons would move on to the next, and therefore resonance is possible here. But as soon as the two electrons of nitrogen, they move here to form a double bond, now nitrogen, instead of having sp3 hybridization, becomes sp2 hybridized, right? It becomes sp2 hybridized. So this nitrogen would have an sp2 hybridized nitrogen, and this nitrogen is sp3 hybridized, right? Then the next thing is, this shows resonance. This does not show resonance. No resonance here. If this shows resonance, resonance pulls the electrons towards the ring, and therefore the electrons are not available now to be lost. A base is a proton acceptor or an electron pair donor. So would it be able to donate the lone pair of electrons? No. Or so therefore, due to resonance also, the electrons, they come into the ring and they stabilize it. And if they stabilize it, it means it's a weaker base. While this one, it has this pair of electrons which are free. There is no resonance. It is sp3 hybridized. Another reason why the S character is lesser. So these electrons are not so strongly bound to the nitrogen and can be lost. Therefore, this would be a stronger base. And if we see here, we said that this is sp3 hybridized. I said that basicity, it increases from top to bottom. So we find that sp3 hybridized is a stronger base, and the sp2 hybridized would be weaker in comparison to the sp3 hybridization. So these were the 5 steps of the mnemonic CARIO that you have to use in order to compare the acidic and basic strengths. Now I'll do just one more video to compare the acidic and basic strengths of some aromatic molecules, and with that we will end the topic. If you found this video helpful, please give it a thumbs up and subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching.